So today we're going to finish section 3.5, which is the mental estimation and approximation. That's the word I want. So mental math and approximation or estimation is the last part of this, and this is about multiplication and division within those regards. So I'm going to flip to my screen. I think we're here. Front-end multiplying. All right, so front-end multiplying is something that you have seen, and I think we see it in proportional and statistical reasoning as well. There's a different, no, we saw it last two or three class periods ago. That's where we saw it. And we did it with estimation is when we did it before. We did front-end estimation with adjustment. That's what we called it. Does that sort of ring a bell, that phrase? I'm not asking if you can tell me what exactly to do with it right now, so no fears. But front-end multiplying will work if the numbers are small enough. So if you get 3-digit, 4-digit numbers, this doesn't work very well. But if you're doing it with smaller numbers, like a single digit times a double digit or something like that, it's not too bad. And so the idea is to take each of the numbers one at a time. So 46 is 40 and 6. You guys should be good with that. We've broken those up multiple times in that fashion. And you multiply each one of them by the other value. And so depending on what the other value is, a 2-digit value might not be a bad value to multiply here, but sometimes it might be like 37 wouldn't be particularly helpful. And so in your head, I think you could probably break apart a 2-digit number and do this in your head, right? 3-digit, 4-digit, you're probably stretching it a little bit. But with 2 digits times a 1 digit, it's not too bad. So what is 40 times 5? 200's correct. And then 6 times 5? 30, for a grand total of 230. So please don't take this to the extreme. If I were to give you an example and ask you to do front-end multiplication or to do some kind of mental math, that's how I would say it. It's mental math with this, and this were like a 5-digit number times a 2-digit number or something. This method doesn't really work very well, okay? Let me show you another one. Compatible numbers. Now we saw compatible numbers when we dealt with addition and subtraction, and in particular we liked to add things together when they added together to be what kind of numbers? Zero, something with a 0 in it. So like 10 or 100, those numbers are what we consider to be compatible. This is very similar. We'd like to multiply numbers together that give us zeros. So maybe we don't get 10, but maybe we get 20. Okay, so we're looking for numbers that multiply together to give us something where there's a 0. And the reason is because if we have, say for example, the number 40 and multiplying by 40 in a later step is a lot easier than multiplying by, say, 42, because 40's really a 1-digit number where we tack on a 0, right? You can use your multiplication tables, those kinds of facts with that. So can you give me, and there's more than one way to do this problem, can you give me 2 numbers here that multiply together nicely? 5 and 2 are fantastic. Those are at the end. This 5 and the 2 are 10, right? Anything else that multiplies together nicely? The 8 and the 5 do as well. And 8 and 5 give me, happens to be 40 on this one, okay? So I'm still left with the 4 in the front. I've got a 40 and I've got a 10. You can move from left to right. You can move from right to left. I don't really care how you move at this point through this particular problem, but because you've got lots of zeros, it makes it easy to work with, right? Now, are there any numbers else that we could have chosen besides 8 and 5 and 5 and 2? 4 and 5 work really nice as well. You get a 20 if you're dealing with 4 and 5. So there's more than one way to deal with compatible numbers sometimes. Sometimes there's not, but oftentimes there is. If I do 4 times 40, what do I get? 160. You guys are like wanting to say it, but you're like, oh, what if I'm wrong? Okay, good. 160, and I've still got the 10 at the end, and then 160 times 10 would be 1,600. Now, maybe not everyone can do this in their head. I'm cool with that. But there are people who could, and quite a few people, because you get those zeros. Those zeros are very, very friendly. Now, if you're using mental math and you think that you're going to do something with a 2-digit number, like if you actually multiplied the 4 and the 8, to give you 32, that's not going to be very doable inside my brain kind of thing. I'm going to have to write something down if I could try to do that, that process first. So we're trying to group things together that work out nicely. And maybe you didn't want to multiply the 4 and the 40 first. Maybe you wanted to multiply the 40 and the 10 first, because then you'd stick with lots of zeros. I mean, you get even more zeros, right? Maybe you choose to do those two first in your head, and then you multiply by the 4 at the end. Any way you do it at this point is pretty nice. This is one of my favorite strategies, and every time that I talk about it, people are like, oh, that's really cool, and then once we get to the test, everybody forgets it. And so not to say that I always put it on the test, but every time I have, people forget it when they get to the test. Thinking money is really cool. You'll notice this is the same problem that we did on front-end multiplying, right? Notice that? Okay. So this is just a second strategy for this one. The nice thing about thinking money is that it works for bigger digits. So the 46 is not very big. Front-end multiplying worked pretty nicely. But if this 46 had been like 3,246, this method works just as well. Whereas front-end multiplying doesn't work just as well. There's too much going on. Okay? So let me show you how this works. This 5, in particular, corresponds to a money amount that you know. What does it correspond to? A $5 bill. I was thinking something smaller. A nickel. A nickel is a really good object for our discussions. This is corresponding to a nickel. So multiplying by 5 is equivalent to having nickels. What if I were multiplying by 25? We'll do it here on example 14 in a minute. Quarters. So this is equivalent to having quarters, okay? So this thinking money method really is just when you're multiplying by 5s and 25s. There's no other sort of coin that's going to help with this particular method, okay? All right, so let's go back to our nickel example. So this is equivalent to saying that I have 46 nickels. And, I mean, that's fine, but, you know, nickels are not near as nice as dimes. It's a lot easier to work with dimes. If I had 46 nickels, how many dimes would that be? How many? 23. How do you get 23? You're right. Why is it 23? Yeah, it's half the number, right? Because it takes 2 nickels to make 1 dime. So we have half the number of dimes. Okay, so if I have 23 dimes, at this point it's equivalent to saying I have 23 times 10 because that's what a dime's worth, right? And multiplying by 10, I mean, that's nice. What is 23 times 10? 230. So going back up to the original problem and thinking about it from here, this is 46 nickels. And I think that it's very reasonable to think that in your head you could say, okay, well, I can divide 46 by 2. It's 23. There's 23 dimes. And 23 times 10 is 230. And I think you can do it just as well with this. Maybe not quite as nice because 32 is not especially friendly because 3 is odd. But you could get there pretty okay. It'd be 1623. Right? 1623 times 10 would be 16,230. So you can do it with a much larger number very nicely because of this unique relationship between dimes and nickels is how we're thinking about it. But really between 5 and 10, that's the relationship that's going on. Think about it this way over here too. Excuse me, here I have 44 quarters. What's a nicer money unit than a quarter? A dollar would be much nicer. So if I took my 44 quarters and I regrouped them into dollars, how many dollars would that be? It would be 11. How did you get 11, Taryn? Yeah. So over here when I went nickels into dimes, I divided by 2. Here when I go from quarters into dollars, I divided by 4. All right? But a dollar, again, is essentially worth 100 pennies or 100 cents. So what would 11 times 100 be? 1,100. Now about you, but I don't want to multiply 44 and 25 together directly. That's really, I'm going to have to write it down. I can't do that directly in my head unless I've got some trick to doing it. And this is a pretty nice trick. Again, it doesn't work for everything, right? Like if this is times 36, I can't think money, okay? But times 25 should be sort of a red flag. Okay, we have a couple of mental math for dividing. This one is called breaking up the dividend. And the idea is to take the value and to break it into pieces that are easier to divide by whatever you're dividing by. So this is a 9, right? So do you see a way to break up 6,318 so that it's more nicely divisible by 9? What do you see? 63 and 18. Those are multiplication facts, right? Those are the multiplication tables. So the idea would be to, again, divide by 9, but instead you would have this written as 63, and that's 6,300, and 18. You can write it like that, or another way to write it, just as another version, is to write it sort of with a vertical bar to remind yourself that, you know, there's two divisions taking place, something like that. I'm kind of actually a fan of putting the plus sign, but your call. Okay, so how many times does 9 go into 63? It would be 7, so how many times will it go into 6,300? 700. So this is 700. And how many times will 9 go into 18? 2. And again, the reason I kind of like the plus is because the plus would continue into the, you know, the division piece above the quotient. So this would be a grand total of what? 702. And that's nice because we look at it and we see 6,300, right? You see the 63, you see the 18, and you know those particular facts. The next one's very similar, but it's not quite as intuitive. You see, on this one, I can't really see two sets of facts that are divisible by 5. Do you see it? I mean, like the 25 at the end is cool, but like 4 is not divisible by 5. But 400 is. So I can break it apart in very much the same way, but I have to think about it a little bit differently. It's much more obvious here. I see the 63. Here, I don't really see the 400 directly, but it still breaks apart that way. So we're going to treat it the same way. So here's the 400 and the 25. So how many times will 5 go into 400? 80. Very good. And how many times will 5 go into 25? 5. And that would be a grand total of 85. And again, we've talked about this before, but just let me remind you, I really do understand that mental math should be in your head. All right? So everything that I've written down on these problems so far today, however many of them I've had, should be things that we're able to compute in our head. That's the goal of these particular methods. For some of us, that's easier than others, and I get that. Okay, but it should be something that's realistic to be done in your head. I just can't see your head. I mean, inside of it, I can see your head, but not inside the head. So you have to write down what you're thinking for me so that I can know whether or not you're doing it in your head. So like, for example, when I do this particular one on tests sometimes, I have students tell me, and I'll do something that's big, like 32,000, or this one here, it'll look like this. And I'll have people tell me, oh, well, I multiplied 3,000 times 5 and 200 times 5 and 40 times 5 and 6 times 5, and then I added it all together in my head, and I think, really? Because I have an advanced degree in math, and I would have a difficult time keeping track of all of that in my head at the same time. Now, writing it down, no problem. If I were writing it down, that would be great. But doing it all in my head, that's a little bit hard to argue. Do you see what I'm saying? So be sure that when you're writing it down that you don't forget what kind of problem you're working with so that you can really justify, yeah, I could do all of that in my head kind of thing, okay? All right, we have a couple more, and they're about estimation. So these are some estimation problems. Okay, so remember, estimation means that the answer is not going to be exact. It's going to be an approximation. So in some fashion or another, I'm abbreviating something, I'm rounding something, I'm chopping something off to make it easier to work with. That's the goal. And oftentimes, we talked about before, estimation is good enough, right? It really is. So it's good to have some estimation strategies that make the math a little bit easier to work with in everyday real life stuff. So here's an example of one. This is 386 times 4. And the idea of this front end estimation, do you see how it says front end? It's the third time we've seen front end. Front end estimation means that we are in fact going to ignore some of the pieces toward the end. We usually keep the first two. So we'd keep the 300 times 4, and we'd keep the 80 times 4, and we'd sort of just ignore the 6. Not because we don't like it, but because we're estimating. We don't need an exact answer. We need an approximation. So front end means eliminating the ending value, or values if it were a longer digit. So what is 300 times 4? 1,200, and 80 times 4? 320, for a grand total of what? 1520. And overall, this is an approximation. You see my double squigglies here, right? An approximation for the original problem up here. Approximate. Okay? So it doesn't really work any differently than any of the other front end kinds of things we were doing. It just makes it fewer steps. Okay? And the last one, compatible numbers. We keep coming back to compatible numbers. They're great. So compatible numbers, again, we could do this particular problem in many different ways, and we are going to get different estimations potentially what we do, and that's okay too. But 4,132 divides by 4 pretty nicely anyway. But it divides by 4 even nicer if I change the 4,132 to a number that's easy to divide by 4. What would be an easy number to divide by 4 that's close? 4,000 would be fantastic. And now maybe you looked at that and you thought of something else, but it's close. Like you thought, well, how about I just do 4,032 and ignore the 100? That'd be okay. I mean, 32 doesn't divide by 4 in a terribly difficult way. But 4,000 is probably your most natural approximation here. And 4,000 divided by 4 would be 1,000. So the approximate value of this should be 1,000. Now, one of the things, and I can't remember who mentioned it when we talked about estimation as being useful, is if somebody were really working this problem out, they should be able to look at this and say, my answer should be about 1,000, and then they should be able to look at their answer that they got if they really worked it out and go, oh, I got 422. 422 doesn't sound very close to the 1,000 I was expecting. I probably made a mistake. Okay, so again, remember estimation does that for us too.